Hello everyone and welcome to this video. In this video, we'll explore hazardous area classification, a concept that plays a vital role in industries such as oil and gas, chemical plants, refineries, power plants, pharmaceutical manufacturing, and many other process industries. In these industries, flammable gases, vapors, or combustible dust may be present during normal operation or because of equipment leaks. If these materials mix with air and encounter an ignition source, they can lead to a fire or even a major explosion. To reduce this risk, hazardous locations are identified and classified, allowing engineers to select electrical equipment that is specifically designed to operate safely in those environments. In this presentation, we'll understand what hazardous areas are, how explosions occur, why hazardous areas are divided into different zones, the different gas groups and temperature classes, and the various explosion protection techniques used in industry. Whether you are a student, a graduate engineer, or a working professional, this video will help you understand the fundamentals of hazardous area classification in a simple and practical way. So, let's get started by understanding what a hazardous area is. Now let's begin by understanding what a hazardous area actually is. A hazardous area is any location where flammable gases, vapors, combustible dust, or fibers are present or may be present in sufficient quantities to form an explosive atmosphere. On the right side of the slide, you can see some of the most common leak sources found in an industrial plant. Let's look at them one by one. First is the storage tank. Flammable vapors can be released through the tank vent during filling, emptying, or normal breathing of the tank. Next is the pump. Pumps use mechanical seals around the rotating shaft, and if the seal wears out or fails, small quantities of flammable liquid or gas can leak into the surrounding area. The flanges and pipe joints are another common leak source. Since these are bolted connections with gaskets, leakage can occur if the gasket is damaged or the bolts become loose. You can also see a manual valve. Over time, leakage may occur through the valve stem packing or internal valve seat. Finally, there's a pressure relief valve or PRV. During an overpressure condition, it opens automatically to protect the equipment by releasing process fluid. If the released fluid is flammable, it can temporarily create a hazardous atmosphere around the discharge point. These are known as potential leak sources because they can release flammable materials into the surrounding air. However, it's important to remember that the presence of a flammable gas or vapor alone does not cause an explosion. An explosion occurs only when certain conditions come together. Let's understand those conditions in the next slide. Now that we've identified the common leak sources, the next question is: how do engineers locate these leak sources in a real industrial plant? The answer is by studying the piping and instrumentation diagram, commonly known as the P&ID. A P&ID is one of the most important engineering drawings used in process industries. It shows the complete process flow, including equipment, pipelines, valves, instruments, and safety devices. Looking at the P&ID on the screen, you can see several pieces of equipment connected through piping. During hazardous area classification, engineers carefully examine this drawing to identify every location where a flammable gas or vapor could potentially escape. For example, they look at pumps with mechanical seals, flanged pipe connections, manual and control valves, pressure relief valves, vents, drain connections, and sampling points. Each of these components is assessed to determine whether it can become a leak source during normal operation or under specified abnormal conditions. Once all the potential leak sources have been identified, engineers evaluate factors such as the type of flammable material, operating pressure, ventilation, and the expected release conditions. Based on this analysis, they determine the hazardous zone surrounding each leak source. So, the P&ID serves as the starting point for hazardous area classification. Before any zone can be assigned, engineers must first understand the process and identify where flammable materials can be released. Now that we've seen where hazardous atmospheres originate, let's understand the three essential elements required for an explosion. Now that we've seen how hazardous areas are identified, let's understand what actually causes an explosion. An explosion can occur only when three essential elements are present at the same time. If even one of these elements is missing, an explosion cannot happen. The first element is fuel. Fuel refers to any flammable substance, such as gases like hydrogen or methane, vapors from petrol or solvents, or combustible dusts like coal dust, flour, or aluminum powder. These materials act as the source of energy for combustion. The second element is oxygen. In most industrial situations, oxygen is supplied by the surrounding air. Since air contains about 21% oxygen, it is readily available in almost every environment. The third element is an ignition source. An ignition source is anything that can provide enough energy to ignite the flammable atmosphere. Common examples include electrical sparks, hot surfaces, open flames, welding operations, static electricity, and even friction between moving parts. When these three elements, fuel, oxygen, and an ignition source, come together in the right proportions, combustion begins. In a confined space, this rapid combustion can generate a dangerous explosion. As shown in the diagram, these three elements form what is commonly known as the fire triangle or explosion triangle. The most important point to remember is that if we remove any one of these three elements, the explosion cannot occur. This simple principle forms the basis of industrial fire and explosion prevention. In hazardous areas, oxygen is already present in the atmosphere, and flammable materials are often part of the process. Therefore, the most practical way to prevent an explosion is to eliminate or control potential ignition sources by using properly certified explosion-protected equipment. In the next slide, we'll look at the common flammable materials found in industrial plants and the ignition sources that can trigger an explosion. Now that we understand the three conditions required for an explosion, let's look at the materials that commonly act as fuel in industrial plants and the ignition sources that can ignite them. First, let's talk about flammable gases. Examples include hydrogen, methane, LPG, propane, and ethylene. These gases are widely used in industries such as oil and gas, chemical processing, refineries, and fertilizer plants. When released into the air, they can form an explosive atmosphere if their concentration falls within the flammable range. Next are flammable vapors. Liquids such as petrol, diesel, solvents, and alcohol do not burn directly. Instead, they produce vapors above their surface. It is these vapors, when mixed with air, that become flammable and can ignite if an ignition source is present. The third category is combustible dust. Many people associate explosions only with gases and vapors, but combustible dust can be equally dangerous. Materials such as coal dust, flour, sugar, aluminum powder, and wood dust can become suspended in the air during handling or processing. If enough dust is dispersed and an ignition source is present, a powerful dust explosion can occur. So, regardless of whether the fuel is a gas, vapor, or dust, the risk arises when it mixes with air in the right concentration. Now let's look at some common ignition sources. Electrical sparks from switches, motors, or damaged cables are among the most common ignition sources. Static electricity, generated by the movement of liquids, gases, or even people, can also produce a spark capable of igniting a flammable atmosphere. Hot surfaces, such as engine exhausts or overheated equipment, may reach temperatures high enough to ignite nearby gases or vapors. Activities like welding and cutting generate sparks and open flames, making them high-risk operations in hazardous areas. Other possible ignition sources include smoking, open flames, friction between moving parts, and even lightning under certain conditions. The key message is simple: if flammable materials are present, every possible ignition source must be identified and controlled. This is the fundamental objective of hazardous area classification and explosion protection. In the next slide, we'll understand why hazardous areas are classified into different zones and how this classification helps improve plant safety. So far, we've learned how explosions occur and the types of fuels and ignition sources commonly found in industrial plants. The next question is, why do we classify hazardous areas? The primary purpose is to prevent fires and explosions by ensuring that electrical equipment installed in hazardous locations cannot become an ignition source. The first and most important objective is to protect people. The safety of plant personnel is always the highest priority. Proper hazardous area classification helps reduce the risk of injuries and loss of life caused by fires or explosions. The second objective is to protect equipment. Explosions can severely damage pumps, motors, electrical panels, pipelines, and other critical plant assets, leading to costly repairs and production losses. Hazardous area classification also helps prevent explosions by ensuring that only equipment specifically designed and certified for hazardous environments is installed in these locations. Another important benefit is reducing plant downtime. An explosion can shut down an entire facility for days, weeks, or even months. By minimizing the risk of ignition, industries can improve the reliability and availability of their operations. It also helps companies meet legal and regulatory requirements. Most countries require hazardous areas to be classified according to internationally accepted standards before a plant begins operation. Ultimately, all of these measures contribute to one goal: improving overall plant safety. To achieve consistency around the world, engineers follow internationally recognized standards. Some of the most widely used standards include IEC 60079, which is used in many countries worldwide, ATX, which is followed across the European Union, NEC, commonly used in North America, and the relevant Indian standards, which are adopted for projects in India. Although these standards may differ in some details, they all have the same objective: identifying hazardous areas correctly and ensuring that the right explosion-protected equipment is installed in the right location. Now that we understand why hazardous areas are classified, let's see how they are divided into different hazard zones based on the likelihood of an explosive atmosphere being present. Now that we know why hazardous areas are classified, the next step is to understand the different hazardous zones. The classification is based on one simple question: how often is an explosive gas atmosphere expected to be present? The more frequently a flammable atmosphere is present, the higher the level of hazard. Let's start with Zone 0. Zone 0 is the most hazardous area. Here, an explosive gas atmosphere is present continuously, for long periods, or very frequently during normal operation. A good example is the inside of a fuel storage tank or the inside of a process vessel containing a flammable liquid. Since flammable vapors are continuously present inside these spaces, they are classified as Zone 0. Next is Zone 1. In Zone 1, an explosive atmosphere is likely to occur during normal operation, but it is not present all the time. For example, the area around a pump mechanical seal, valve, or sampling point may occasionally experience the release of flammable gas or vapor during normal plant operation. Because these releases are expected to occur from time to time, these locations are typically classified as Zone 1. Finally, we have Zone 2. Zone 2 is the least hazardous of the three gas zones. Under normal operating conditions, an explosive atmosphere is not expected to be present. If it does occur, it is only due to an abnormal event, such as equipment failure, and it remains present only for a short duration. A typical example is the area surrounding a Zone 1 location. Normally, no flammable gas is present there. However, if an unexpected leak occurs and the gas spreads briefly before being dispersed by ventilation, that surrounding area may be classified as Zone 2. So, to summarize, Zone 0 means the explosive atmosphere is present continuously or for long periods. Zone 1 means it is likely to occur during normal operation. And Zone 2 means it is not likely during normal operation, and if it does occur, it exists only for a short time. Understanding these zones is essential because the type of electrical equipment that can be installed depends directly on the zone classification. The higher the hazard level, the more stringent the equipment protection requirements. In the next slide, we'll look at gas groups and understand why different flammable gases require different levels of explosion protection. We've now understood how hazardous areas are divided into different zones. The next concept is gas groups. You might think that all flammable gases behave in the same way, but that's not true. Some gases require only a very small amount of energy to ignite, while others are relatively less sensitive. Because of these differences, flammable gases are classified into different gas groups. As shown on the slide, Group I is used for underground mining applications, where methane, also known as fire damp, is commonly encountered. Equipment designed for mining has different construction requirements because of the unique hazards present in underground mines. For most industries such as oil and gas, petrochemical plants, refineries, power plants, and chemical industries, we use Group 2 equipment. Group 2 is further divided into three categories: IIA, IIB, and IIC. Let's start with Group IIA. This group includes gases such as propane. These gases are comparatively less easy to ignite and therefore require the lowest level of protection within Group 2. Next is Group IIB, which includes gases such as ethylene. These gases are more hazardous than Group IIA because they require less ignition energy. As a result, the equipment design requirements become more stringent. Finally, we have Group IIC, which includes gases such as hydrogen and acetylene. These are among the most hazardous gases because they ignite very easily and can pass through extremely small gaps. Equipment intended for Group IIC applications must provide the highest level of explosion protection. An important point to remember is that equipment certified for a higher gas group can generally be used for lower gas groups. For example, Group IIC equipment can also be installed in IIB and IIA hazardous areas, provided all other certification requirements are satisfied. So, in terms of increasing hazard, the order is IIA, then IIB, and finally IIC, with IIC requiring the highest level of protection. In the next slide, we'll learn about temperature classes and understand why controlling the surface temperature of electrical equipment is just as important as preventing sparks. So far, we've learned about hazardous zones and gas groups. The next important concept is the temperature class. Many people assume that a spark or an open flame is always required to ignite a flammable gas. However, that's not always the case. If the surface of an electrical device becomes hot enough, it can ignite a flammable gas or vapor without producing any spark at all. This is why every explosion-protected electrical equipment is assigned a temperature class, often referred to as the T class. The purpose of the temperature class is simple. It specifies the maximum surface temperature that the equipment is allowed to reach during normal operation. As shown in the figure, the surface temperature of the equipment must always remain below the auto-ignition temperature of the surrounding flammable gas or vapor. Let's understand this with a simple example. Suppose a particular gas has an auto-ignition temperature of 200 degrees Celsius. If the surface of a motor or junction box reaches to 0 degrees Celsius, the gas can ignite even though there is no spark or open flame. On the other hand, if the equipment surface temperature remains well below 200 degrees Celsius, the gas will not ignite due to the hot surface. This is why selecting the correct temperature class is just as important as selecting the correct hazardous zone or gas group. During equipment selection, engineers compare the auto-ignition temperature of the hazardous gas with the maximum surface temperature of the equipment. The equipment is considered suitable only if its maximum surface temperature is lower than the ignition temperature of the gas. In the next slide, we look at the different explosion protection techniques that allow electrical equipment to operate safely in hazardous areas. Now that we've understood hazardous zones, gas groups, and temperature classes, the next question is: how can electrical equipment operate safely in a hazardous area? The answer lies in explosion protection techniques. Electrical equipment such as motors, junction boxes, lighting fixtures, sensors, and transmitters can produce sparks, arcs, or hot surfaces during normal operation. In a hazardous area, these can become ignition sources. To eliminate this risk, manufacturers design equipment using different explosion protection techniques. Each technique prevents the surrounding flammable atmosphere from being ignited in a different way. As shown on the slide, there are several commonly used protection methods. The first is XD flameproof. In this method, the equipment enclosure is strong enough to withstand an internal explosion and prevents the flame from spreading to the surrounding atmosphere. Next is XE increased safety. Instead of containing an explosion, this method prevents one from occurring by eliminating potential ignition sources through improved electrical and mechanical design. Then we have XI intrinsic safety. This technique limits the electrical energy in the circuit so that even under fault conditions, there isn't enough energy to ignite a flammable atmosphere. Another method is XP pressurization. Here, the enclosure is continuously supplied with clean air or an inert gas at a pressure higher than the surrounding atmosphere. This prevents flammable gases from entering the enclosure. We also have XM encapsulation, where electrical components are completely enclosed in a protective resin. Since the live parts are sealed, the surrounding hazardous atmosphere cannot come into contact with them. Finally, there is XN non-sparking. This protection method is intended for zone to hazardous areas where explosive atmospheres are not expected during normal operation. The equipment is designed so that it does not produce sparks or excessive temperatures under normal operating conditions. Each of these protection techniques has its own applications, advantages, and limitations. The appropriate method depends on the hazardous zone, the type of gas present, and the equipment being used. In the next few slides, we'll look at each protection technique individually, starting with one of the most widely used methods in industry, XD flameproof protection. Let's begin with one of the most widely used explosion protection techniques in industry, XD flameproof protection. The term flameproof does not mean that an explosion cannot occur inside the equipment. In fact, the equipment is designed with the assumption that an explosive mixture may enter the enclosure and be ignited. The key objective of XD protection is to ensure that if an internal explosion occurs, it does not ignite the hazardous atmosphere outside the enclosure. Let's look at the illustration on the screen. Inside the enclosure, you can see an explosion taking place. The pressure and temperature inside the enclosure increase rapidly. In a normal enclosure, this explosion could force hot gases and flames directly into the surrounding atmosphere, causing a much larger explosion. However, in an XD flame-proof enclosure, this does not happen. The enclosure is built with strong mechanical construction so that it can safely withstand the pressure generated by the internal explosion without rupturing. Now notice the narrow joint between the enclosure body and the cover. This is called the flame path. When the hot gases produced by the explosion try to escape, they must travel through this long and narrow flame path. As they move through this passage, the metal surfaces absorb heat from the gases. By the time the gases reach the outside, their temperature has dropped below the ignition temperature of the surrounding flammable atmosphere. As a result, no external explosion occurs. So, XD protection works on two important principles. First, the enclosure is strong enough to withstand an internal explosion. Second, the flame path cools the escaping gases before they reach the hazardous atmosphere outside. Because of its robust construction and high level of protection, XD equipment is commonly used for motors, lighting fixtures, junction boxes, control stations, and other electrical equipment installed in Zone 1 and Zone 2 hazardous areas. In the next slide, we'll look at another protection technique called XE, increased safety, which prevents ignition by eliminating potential ignition sources instead of containing an explosion. Now let's look at another widely used protection technique called XE, increased safety. Unlike XD flame-proof protection, where the enclosure is designed to contain an internal explosion, XE follows a completely different approach. The basic principle of XE is prevention rather than containment. The equipment is designed so that, during normal operation, it does not produce sparks, electrical arcs, or excessive surface temperatures that could ignite a flammable atmosphere. As shown on the slide, this is achieved through several important design features. The first feature is enhanced insulation. High-quality insulation reduces the possibility of electrical faults that could create sparks or short circuits. Next are increased creepage and clearance distances. These are the minimum distances between live electrical parts. By increasing these distances, the risk of electrical tracking or flashover is significantly reduced. Another important feature is secure, vibration-resistant terminals. In industrial plants, equipment is often subjected to continuous vibration. Loose electrical connections can generate heat or sparks, so XE equipment uses specially designed terminals that remain secure during operation. The equipment is also designed with controlled surface temperatures, ensuring that no external surface becomes hot enough to ignite the surrounding hazardous atmosphere. In addition, XE enclosures are typically IP rated, providing protection against dust and moisture. This helps maintain the reliability and safety of the electrical components inside. Because XE equipment is designed to prevent ignition, it is commonly used for electric motors, junction boxes, terminal boxes, lighting fixtures, and cable glands, as shown on the slide. This protection method is suitable for Zone 1 and Zone 2 gas hazardous areas, where equipment must operate safely without becoming a potential ignition source. To summarize, XD allows an internal explosion but safely contains it, whereas XE is designed so that an internal explosion is not expected to occur at all. This is the fundamental difference between these two protection techniques. The next explosion protection technique is XI, intrinsic safety. Unlike XD, which contains an explosion, or XE, which prevents sparks through improved design, XI works by limiting the electrical energy available in the circuit. The principle is very simple. Even if a short circuit, loose connection, or equipment fault occurs, the voltage and current are restricted to such low levels that they cannot generate enough energy to ignite a flammable gas or vapor. In other words, an ignition source is eliminated by design. This is usually achieved by using intrinsic safety barriers or galvanic isolators, which are installed between the safe area and the hazardous area. These devices limit the voltage and current that can reach the field equipment. As a result, even if a fault occurs in the hazardous area, the electrical energy remains below the minimum ignition energy of the surrounding flammable atmosphere. Because of this high level of safety, XI protection is widely used for instrumentation and control systems. Typical examples include pressure transmitters, temperature transmitters, flow transmitters, level transmitters, proximity sensors, switches, and other field instruments. One of the biggest advantages of XI equipment is that maintenance and testing can often be carried out without completely shutting down the plant, provided the appropriate safety procedures are followed. This helps reduce maintenance time and improve plant availability. However, XI protection is generally used for low-power electrical circuits. It is not suitable for high-power equipment such as motors or large electrical heaters, which require much higher electrical energy to operate. To summarize, the principle of XI intrinsic safety is straightforward. If there isn't enough electrical energy to ignite the hazardous atmosphere, an explosion cannot occur. The next explosion protection technique is XP, pressurization. Unlike the protection methods we've discussed so far, XP does not rely on containing an explosion or limiting electrical energy. Instead, it prevents a hazardous atmosphere from entering the enclosure in the first place. The principle is quite simple. The enclosure is continuously supplied with clean air or an inert gas, such as nitrogen. This creates a positive pressure inside the enclosure that is higher than the pressure of the surrounding atmosphere. As shown in the illustration, the clean air enters the enclosure and keeps the internal pressure slightly higher than the outside. Because of this pressure difference, flammable gases or vapors from, even if there are small gaps around the door, cable entries, or joints, the airflow is always directed from inside to outside, preventing the hazardous atmosphere from flowing inward. Since no flammable gas is allowed to enter the enclosure, electrical equipment inside, such as contactors, relays, variable frequency drives, PLCs, or control panels, can operate safely without creating an explosion hazard. To ensure continuous safety, the enclosure is equipped with pressure sensors and monitoring devices. If the internal pressure falls below the required level, the electrical supply is automatically disconnected to prevent unsafe operation. XP protection is commonly used for large electrical control panels, analyzer cabinets, motor control centers, PLC enclosures, and other equipment that cannot easily be designed using XD or XE protection. In summary, the principle of XP pressurization is straightforward: maintain a clean, positively pressurized enclosure so that flammable gases cannot enter and come into contact with energized electrical components. In the next slide, we'll look at XM encapsulation, where electrical components are completely sealed inside a protective resin to isolate them from the hazardous atmosphere. The next explosion protection technique is XM encapsulation. As the name suggests, encapsulation means that the electrical components are completely enclosed within a protective insulating material, usually a specially formulated resin. The basic principle is very simple. Instead of allowing the hazardous atmosphere to come into contact with live electrical parts, the components are permanently sealed inside the resin. Since the flammable gas or vapor cannot reach the energized components, ignition cannot occur. As shown in the illustration, the electrical components are fully surrounded by the encapsulating material. This protective layer not only isolates the live parts from the hazardous atmosphere but also provides excellent mechanical protection against moisture, dust, vibration, and corrosion. Even if the components generate small sparks or heat internally, these remain confined within the encapsulated material and cannot ignite the surrounding atmosphere. Because of its compact design and high reliability, XM protection is commonly used for electronic circuits, sensors, transformers. One important point to remember is that encapsulated components are generally not repairable. If the internal electronics fail, the entire encapsulated unit is usually replaced rather than repaired, since removing the resin would damage the protection. To summarize, the principle of XM encapsulation is simple: completely seal the electrical components inside a protective resin so that the hazardous atmosphere can never reach the energized parts. The final explosion protection technique we'll discuss is XN non-sparking. As the name suggests, XN equipment is designed so that, during normal operation, it does not produce sparks, arcs, or excessive surface temperatures that could ignite a hazardous atmosphere. It's important to understand that XN protection is intended only for Zone 2 hazardous areas. Why only Zone 2? Because in Zone 2, an explosive gas atmosphere is not expected during normal operation. If it does occur, it is only due to an abnormal event, such as an unexpected leak, and it exists for a short period of time. Since the probability of a hazardous atmosphere is relatively low, the protection requirements are also less stringent than those for Zone 1. To achieve this level of safety, XN equipment is carefully designed and manufactured to eliminate potential ignition sources during normal operating conditions. It also ensures that the equipment surface temperature remains within safe limits. Typical applications include lighting fixtures, terminal boxes, junction boxes, control stations, and certain types of electrical motors installed in Zone 2 locations. However, XN equipment must not be used in Zone 0 or Zone 1, where a flammable atmosphere is present continuously or is likely to occur during normal operation. In those areas, higher levels of protection, such as XD, XE, or XI, are required. So, to summarize, XN protection is based on preventing ignition during normal operation and is specifically intended for Zone 2 hazardous areas, where the likelihood of an explosive atmosphere is low. With this, we've covered the major explosion protection techniques commonly used in hazardous areas. In the next slide, we'll see how all this information is represented in the equipment marking found on explosion-protected electrical equipment. We've now reached the final topic of this presentation, equipment marking. Every electrical equipment designed for use in hazardous areas carries a marking like the one shown on the screen. At first glance, it may look complicated, but once you understand what each part represents, you can quickly determine where the equipment can be safely installed. Let's read this marking from left to right. The first number is 0032. This is the Notified Body Identification Number. It identifies the certification body that tested and certified the equipment according to the applicable explosion protection standards. Next is Group 2. As we discussed earlier, Group 2 equipment is intended for surface industries, such as oil and gas, chemical plants, refineries, power plants, and pharmaceutical industries. Group I equipment, on the other hand, is used in underground mining applications. The next marking is to G. The number 2 represents the equipment category, indicating that the equipment is suitable for Zone 1 hazardous areas. The letter G stands for gas, meaning this equipment is certified for use in gas or vapor hazardous atmospheres. If the equipment were designed for combustible dust, you would see the letter D instead. Next comes XDB. The letters X indicate that the equipment is certified for use in explosive atmospheres. The designation DB tells us that the equipment uses flame-proof protection. This means the enclosure is designed to withstand an internal explosion and prevent the flame from propagating to the surrounding hazardous atmosphere. The next marking is IIB, which represents the gas group. As we learned earlier, Group IIB includes gases such as ethylene. It requires a higher level of protection than Group II, but is less demanding than Group IIC. Next is T4, which indicates the temperature class. A T4 rating means that the maximum surface temperature of the equipment will not exceed 135 degrees Celsius during operation. This ensures that the equipment surface remains below the auto-ignition temperature of the surrounding gas. Finally, we have GB, which stands for the Equipment Protection Level or EPL. The EPL indicates the level of protection provided by the equipment. A GB rating means the equipment provides a high level of protection and is suitable for installation in Zone 1 gas hazardous areas.